So in this section, we're going to look at simple harmonic motion and damped motion, which is basically taking a sine curve or taking a cosine curve. And first of all, understanding that it's the unit circle unrolled. So we call it a projection on the XY coordinate plane. But also noting that we've got simple harmonic motion if there's no friction involved, meaning there's no air friction, there's no gravity, there's nothing to bother it. It's damped motion if there is something that's going to bother it. So what is it, you ask? For instance, if you've got a spring, and you pull the spring down and you let go. You can't see my hands. You pull the spring down and you let go. That spring is going to go up, down, up, down, up, down, up, down, up, down. Okay, so that is an example of simple harmonic motion, as long as you realize that eventually it's going to stop. It's going to come back to a resting position. And so on the first few problems that we do, we're going to assume that there's no friction. We're going to assume that we have, hang on, I'm distracted very easily. We're going to assume that things will go on forever and ever and ever in alternity. Damped motion is what's going to occur when I take that spring and go up, down, up, down, up, down, up, down, and then pretty soon it's just going to settle back into its resting position. But again, simple harmonic motion is what does this stuff look like to start with. You should recognize these formulas from the first page of the notes that I gave you back in chapter, I don't know, like the first week or so, when we were starting to graph. Okay, so you'll notice that we have an amplitude. We have either a sine or a cosine function, because remember that cosine is simply a transformation of sine. But you'll notice that for our purposes, for simple harmonic motion, we are not including any horizontal or vertical transformations. Okay, so we are simply looking at amplitude, and we are looking at what the coefficient would be that affects the period. So for these notes, I've simply reworked it where instead of having a b, which is what we had before, I have an omega, and instead of using x, we're using t for time. Okay, so amplitude is still half the total height of the wave. The period is still going to be found by dividing 2 pi by the coefficient on t. And then frequency is going to be how many cycles are completed within 2 pi, which would be the original period. Okay, so it's essentially going to tell you how fast or how slow this is going. Now this mess down here is what we're going to use for damped motion. And we're in terms of t. Okay, d is going to be for distance or displacement. M is your mass, so m occurs here and it occurs here. T is going to be time in seconds unless you're told otherwise. B is your damping factor or your damping coefficient. And then omega is going to be your angular speed. And again, that's going to be used to calculate the period and the frequency. So the one thing that you need to notice on this, first of all, remember that E is a number. It's not a variable. And second of all, notice that T is being multiplied to the radical. So T is not underneath that radical. But what we'll do in our first few examples is first of all decide if we're going to use sine or cosine. So looking back at our sine curve, it essentially looks like this. Okay, but it goes on and on forever that way, and it goes on and on forever this direction. And then our cosine curve will usually, or not usually, it starts at the top and then comes down, and then it starts at the top and then goes down. Okay, so what does this mean? So when should I use sine? When should I use cosine? If you are starting to figure out your simple harmonic model, and if you're starting from rest, then this thing is projected up or it's pulled down or whatever. But when t equals 0, when t equals 0, you are at rest. Okay? Then you're going to use sine. If you're told otherwise, if you're told, okay, I pulled this spring up or I pulled this spring down, then you'll know to use cosine, because this is where you're going to be when the spring or when the tuning fork or whatever you're looking at, whenever that thing is at rest. That's what you're looking for. So on these first few, when we go through, we are simply going to use these two equations up here. We're going to have to decide if it's sine or if it's cosine. And then we'll look at the damping, the damping motion, the damped motion. I cannot think. Here we go. So if I have an amplitude of 3, so notice that's in absolute values, okay, and if I know that the period is 2 seconds, so where am I getting this information? From the first problem. So it says an object attached to a coiled spring is pulled down a distance, A, so it's pulled downward from its rest position, and then it's released. Assuming that the motion is simple harmonic with a period of t, write a function that relates the displacement d of the object from its rest position after t seconds. Assume that the positive direction of motion is up. So first of all, what do we know? We know that this is going to be cosine, because I am told immediately that this was pulled down and then it was let go. Okay, it was pulled down and then it was let go. I'm also told that the amplitude, okay, or the distance that it was pulled down to is 3. So I know a couple of things right now. I know that it's a negative distance because I pulled it down. I know that my amplitude is 3. I know I'm dealing with cosine because it's not starting from rest. It's not starting from rest. So the only thing I've got left to figure out, because remember we're in terms of t, is what is omega? What's the coefficient on t? So this goes back to what we did before. Normally we would say 2 pi over b, but we're going to say 2 pi over omega gives me a period of 2. So 2 pi over omega gives me a period of 2. So when I cross multiply, I get 2 pi equals 2 omega, and then divide both sides by 2. And so I end up with omega is pi. So you have now figured out your equation for your simple harmonic motion. So let's try another one. We have, hang on, flipping papers. We have an object is attached to a coiled spring and it is pulled down a distance, A, and my A is going to be 6, okay, from its rest position, and then it's released. Assuming that the motion is simple harmonic with a period of t, write the function that relates the displacement, or the distance, d, of the object from its rest position after t seconds. Assume that your positive direction of motion is up. So I know that A is 6, and I know that the period is 3 pi seconds. Okay, the period is 3 pi seconds. So what do I know first of all? I know that this thing was pulled down. It was pulled down 6 units. So I know that I'm going to have a negative, which signifies downward movement. I know the amplitude is 6. I know I'm dealing with cosine because I'm not starting from rest. I'm starting from a pulled down position. And then I just need to figure out what omega is. So if t is 3 pi, then 2 pi over omega should give me 3 pi. So I need to cross multiply. So 2 pi is 3 pi times omega. Divide both sides by 3 pi. Any number divided by itself is 1, so I get a coefficient of 2/3. Okay, so let's try it again. We have, it's pulled down a distance of 7 centimeters from its rest position. So I know that A is 7. It's released. My period is 2 seconds. Write an equation that relates the displacement of the object from its rest position after t seconds. Be very careful. Also assume that the positive direction of the motion is up, and at time where t is 0, the object is at its resting position, and then we'll move down. So I now know that I'm starting at rest, and then it's going to move in a downward position. So I know that this is sine, and I also know it's negative. Okay, so it's not propelled upwards, it's pulled downwards. So I know that this is going to be a negative. My amplitude is 7, and I'm dealing with the sine curve because I am told that when t is 0, my object is at rest. Okay, so again, all I need to find is the coefficient on t. So I know that 2 pi over omega is going to be 2. So cross multiply. 2 pi is 2 omega. Divide both sides by 2. And you'll find out your coefficient on t is pi. I almost wrote omega. All right, one more time. And then we will introduce the next part before we go to a second video. So I know that it's pulled down 8 centimeters. So my amplitude is 8. I know it's pulled down in a downward motion. And I'm also told that when t is 0, the object is at rest, and then it will be pulled into a downward position. So the only thing I don't know is what is the period. The period is 2 pi. So what do I know? I'm starting from rest, so I know that this is the sine function. I'm moving in a downward motion, so I know it's negative. I know my amplitude is 8, so it's going to be displaced by 8 centimeters or 8 whatever's it is, 8 centimeters, okay? And now I just need to find the coefficient on t. So I know that 2 pi over omega is the same thing as 2 pi. So omega is going to be 1, but just in case you don't see that yet, we've got 2 pi equals 2 pi times omega. Divide both sides by 2 pi. And omega must be 1. So that's your final answer. Okay. So now what we want to look at is damped vibration curve. So I might as well tell you really quick what damped vibration is. If you think about, look up on YouTube and look up the bridge in Washington that fell. Okay, it's a black and white video. It's about 1 minute and 14 seconds long. And I think it's called the Tacoma Narrows Bridge, if I remember right. And you will find out why this type of motion is important. Because if engineers don't take wind and sound and that type of stuff into account, then bridges fall or buildings fall. Think about an earthquake and the vibrations that an earthquake will cause. It'll cause buildings to fall. So those are all things that need to be taken into account. But this bridge was built, I want to say back in the 50s, 50s or 60s maybe. And it was, the wind was 35 miles per hour that day, which is a nice brisk wind. But it caused the bridge to start swinging. And you can actually see the waves. And it's really, really cool. But it's also very sad because it shows a car. Why am I drawing a car? It shows a car on the bridge. And what you don't know is that there's a dog in the car and it's afraid. And so you see a man walking away from the car and he had tried to save the dog, but the dog was scared, so it attacked him. And so when the bridge falls into the water, the dog died. That makes me sad. Anyway, but this is an example of why studying damped motion and simple harmonic motion is actually extremely important, because if you don't, your bridge is going to fall. So I'm going to show you some examples in the next video.